Hello, my name is Mohammad Vahidinia from ISBS Iran, and I will present our work on covariance charge in different market invariant theories of gravity, such as general relativity, and its implication for black hole thermodynamics. This research is the result of a collaboration with these people, and I encourage you to also check out the related poster presented by my colleague Vahid Taghi. As you know, GR has two properties: equivalence principle, which ensures space-time covariance, and the background independence, meaning all background geometries are solutions of same theory, or equivalently, general covariance over the space of solutions. These features, while elegant, lead to the problem of charge covariance in GR. To separate these two notions of covariance, we turn to the covariance phase space formalism. The covariant phase space formalism provides a systematic framework for defining charge variation associated with symmetries. In a theory like GR, it takes a diffeomorphism as a symmetry and a solution and gives the corresponding charge variation. However, this framework has some limitations. It does not guarantee that the charges are integrable, and it assumes fixed boundaries that breaks the covariance slightly. To address this issue, we extend the covariance phase formalism to allow boundary fluctuations, where boundaries are not fixed and its variation does not vanish. This restores covariance and, more interestingly, ensures the integrability of charge. This charge can now be expressed as the nodal charge plus the integration constant. While the nodal charge is covariant, the integration constant, which is a constant function over the solution space, breaks of covariance because it depends on a reference field. It is important to note that this constant is actually the origin of the non-covariance of the charge in this framework. These subtleties are discussed further in Vahidiania's poster. We applied our framework to charge associated with Kling vectors and proved two theorems that establish rigorous bases to get the smart relation and the first law of black hole thermodynamics. The first theorem is actually a balance equation. We have shown that for any Killing vector, the difference in nodal charge between two codimension two surfaces, like S1 and S2, equals the integral of the Lagrangian over the connecting surface. For Killing horizon generators, this leads to the smart relation. The second theorem presents a conservation equation. It says that a combination of charge variation and a flux term can be defined in a way that they are independent of the location of the codimension two surfaces. This implies temporal conservation for time-like separation and a kind of radial conservation for space-like separations. Now we are ready to derive the smart formula and the first law. To do this, we calculate the charge associated with the generator of blind horizon and apply the two theorems to obtain a smart relation and the first law. Note that due to the flux term in definition of K, the ADM mass appears in the first law, while the smart formula is expressed in terms of the nodal mass. However, by adding the appropriate boundary terms to the Lagrangian, the smart relation can be written in terms of the ADM mass as well. It is important to emphasize that although definition of the charge in covariant phase-space formalism and the overgeneralization involves certain ambiguities, the resulting smart relation and the first law are free from them. Interestingly, the smart formula represents a Legendre transformation of the energy, which is equal to the free energy of the system and is directly related to the on-shell action. Finally, it is worth noting that these results are valid for arbitrary surface or cross-section of the horizon. Thank you for your attention.